So far, we have done the following thing. We have defined dynamical systems. So we defined a state space, we defined a law of motion. We studied what one trajectory can do. That we do by integrating equations of motions or by mapping a system that's defined in discrete time. Then we stepped a little bit further out and we started exploring the neighborhood. So we spent some time on linear stability. And that tells us not what one trajectory does, but what a neighborhood of trajectories does. And the main message was that if you have evolution in time, you should really work in Poincare sections because they capture all important transverse dynamics. Well, dynamics along the trajectories is not quite as interesting. And then there was a detour, which I think is very important, which is a technical detour, but it says that if you have a symmetry in your system, you should use it. It's kind of technical, and by 2 weeks of that stuff, you might have forgotten why we were here in the first place. So now I return to the main narrative. So now I assume that you know that when you have time evolution, you should look at Poincare sections, a bold assumption. And that if you have discrete symmetries, you should look at symmetry in fundamental domain. And if you have continuous symmetries, then you should slice them. And if you have combination of both discrete and continuous symmetries, which most of the time you do in your research project, in theoretical physics at least, then and experimental, then you should quotient both the discrete symmetry and continuous symmetry. And now we are ready to continue our narrative. We've gotten rid of all these nuisances that symmetries induce, and now I assume we have a desymmetrized system, and how do we analyze it? And the main issue, as you will realize when you have chaotic dynamics, it doesn't make sense to analyze individual trajectories. I mean, you learn a lot just by running a computer, but it doesn't give you a good description of long-time behavior for chaotic systems.